Alright, so for this one we're going to look at a problem involving circular motion. So this is one you can do yourself. You can actually take a water bottle, drink a little bit of the water out of it, pop the cap open, and spin it around in a vertical circle. And the idea is if you spin it fast enough, even when it's at the top of the vertical circle that you're spinning it in, water won't fall out. And so it's possible to spin this thing fast enough that the water won't actually fall down and get you wet, as it's pulled down by gravity directly above your head. Spin too slowly and it's going to fall out, and you're going to get wet by it. So here we have a case in which you're spinning a water bottle in a vertical circle. You're given the radius of the vertical circle, the mass of the water, and you're told that gravity is always pulling down on the bottle and on the water in the bottle. And what you're asked for is how fast do you have to spin this when it's right above you, so inverted so the water is ready to fall out, to not get wet. And at this point, you can also figure out the normal force that must be exerted by the bottle when you're right above it. Now, this is a case in which we are trying to maintain uniform circular motion. So we're going to be using these elements. I'm going to actually solve this problem twice, once in the centripetal picture and once in the centrifugal picture, to show you the difference between the two different pictures. Both are equally valid. It's up to you to pick whichever one makes the most sense to you. Now, regardless of which one that you pick, the starting point for both of them is the same. So we're going to do this right off at the start. At the end of the day, this magnitude of centripetal or centrifugal force is going to give us how big of a force we're going to get via the circular path. And we're going to be using it in either case. So the first step is literally just to write it down. Now, the second step is to look at the two different pictures. So we're going to start off with the centripetal picture. This is not my favorite one, but it is one you can use to deal with this. So in the centripetal picture, we have this magnitude of the force. Our centripetal force, so our Fc, is radially inward. And our Fc must be equal to the net force. So I don't want to underline that, I want to bold it. Our net force must equal to the centripetal force. Like so. Now, when you're dealing with this, the simplest case would be just for this net force to equal to this centripetal force. In other words, to use the centripetal magnitude here to just determine what the net force needs to be. Now, in the simplest case, if we take a look at the forces that act on this particular water bottle, we have the force of gravity being downward. So in the simplest case, we would require no other forces besides gravity, and this gravitational force would be the only force that equals to the net force. Because in the centripetal picture, this centripetal force just tells us what the net force needs to be. It doesn't tell us or doesn't provide us with an additional force to add to our question. So putting these two relationships together, what we would find is that the centripetal force must equal to the gravitational force in the minimum case. So we have equations for both of these. For the centripetal force, we have mv squared divided by r. And for the gravitational force, we have m multiplied by the acceleration due to gravity. Like so. Now, you can put in all the numbers if you like, but what you'll notice here is there are masses on both sides, so we can cancel them out. And we know that this acceleration due to gravity here, these are all just scalars, are going to match up with one another, because if you'll notice, the gravitational force and the centripetal force are pointing in the exact same direction. So with this being said, we can solve this. We have v squared divided by 0.7 meters is equal to 9.8 meters per second squared. Like so. We can then solve for v here. So if we solve this, what we'll get is v is equal to around 2.6 meters per second. And that's how fast, in terms of tangential speed, we're going to need to spin this around to not get wet. If we spin it faster, we will need to have a different or an additional force created by the normal force that keeps this thing together. Now, in this case, we're looking at the minimum case. The only force we need is the force of gravity, and therefore the normal force will be 0. So that's the centripetal picture. This picture, though, not exactly my favorite. So what we're going to do is we're going to reset this, and we're going to take a look at the centrifugal picture, which I've been told makes a lot more sense to most people. All right, so in the centrifugal picture, again, we're going to start with the same characteristic equation for determining its magnitude. The difference here, however, is we are the water. So you can put yourself, in the water. Let's just draw a little X. I'm not drawing a stick figure here, but you are the water in this case. Now, in the centrifugal picture, you are the water. So when this centrifugal force actually will push you radially outwards, like so. Now, gravity is still here, so gravity is still going to pull you downwards. Doesn't matter if you're looking at this externally or internally, you'll still see yourself be pulled down by gravity. Now, the goal here is to look for the lowest or the easiest point at which you don't get wet. So if you are the water, you're going to want to not move, right? And that's the key behind this centrifugal picture. You are the thing in question. You can pretend that you're the thing in question. Now, if you're the thing in question here, and we don't want you to fall out of the bottle or have to be pushed by something else, what I can tell you is that for you, being the bottle itself, the net force has to be equal to 0. Now, again, in the simplest case, we don't really want the bottle itself to have to exert a normal force to keep us here. So this net force should be made up of 2 separate forces, right? Because we are the water. If we're the water, we feel ourselves be pulled down by gravity, and we also feel ourselves be pushed towards the outside edge of the container. Just like if you take a very sharp turn, you'll see yourself be pushed outwards. And because we're the bottle, we need this to add up to 0 in the minimum case. Now, if we spin this faster, we could add in a normal force to make up the difference, but if we're the water and we're not going anywhere, we should see this net force be 0 in all of these cases. Now, in this particular instance, the force of gravity is 0 in the vertical, and you can take the mass of 0.25 and multiply it by the acceleration due to gravity, 9.8 meters per second squared down, and this will give you a vertical force for the force of gravity. When this is added to the centripetal force, this must equal to 0, and this tells us that the centripetal force must be upwards, which we identified from our diagram, and must have a strength of 2.45 newtons. All right, so what you'll notice here is in the centrifugal picture, we've actually just added in an extra force due to how quickly we are spinning. Now, from this, just like before, we can extract out our speed in much the same way. The magnitude of our force needs to be equal to mv squared over r, and this must equal to 2.45. Just like before, we can put in the radius, we can put in the mass, and we can solve for v. If we solve for v, we will again get 2.62 meters per second. And here, since we're looking at the minimum case, we don't want the bottle to have to exert anything. Now, if we did have a normal force, right, the centrifugal picture is again pretty straightforward because all we would have to do, as always, if we had a normal force, would be to add the normal force in. So it's up to you which picture you choose. The centripetal picture involves the net force must equal to the centripetal force. In the centrifugal picture, you are the thing that's spinning, so this centrifugal force is an extra force that you're going to add to your system when doing your problem solving. So it's up to you which one you pick. Both of them work. However, in the past, most people have preferred doing their problems in a centrifugal picture. That way they can use the same technique as if your thing, is staying where it is. Your net force is going to be zero. If you do have a net force, you can use that to determine the acceleration in the frame of reference of whatever the thing in the centrifuge is moving at. But both of them work. You can pick either one.